carbon combines with other atoms such as hydrogen, nitrogen, oxygen, and sulfur to form structural units called functional groups. Functional groups are important for three main reasons. First, they are the units by which we divide organic compounds into classes. Second, functional groups they act as the sites of characteristic chemical reactions. So it means that a particular functional group in all organic compounds will undergo same type of chemical reaction. And thirdly, functional groups serve as a basis for naming organic compounds. In this chapter, we will introduce several of the functional groups which we will encounter later in this course. At this point, our concern is only with the pattern recognition. We shall have more to say about the structure and properties of these functional groups in following chapters. So right now we will only focus on the name and formula of the functional group. So let's start with the first functional group, which is alcohol. The alcohols are those organic compounds which contain hydroxyl functional group. The formula of hydroxyl or alcohol functional group is OH. Alcohols are classified as primary, secondary, or tertiary alcohol depending on the carbon atoms bonded to the carbon bearing the OH group. For example, in this case, this is the carbon which bears the OH or hydroxyl functional group. This carbon contains only one more carbon-carbon bond, hence it is a primary alcohol. So in the second example, this carbon which bears the OH is bonded to two more carbon. So in other words, it contains two more carbon-carbon bonds. So hence it is a secondary alcohol. And finally, by now you have already guessed it, that this carbon which bears the OH function group contains three more carbon-carbon bonds. Therefore, it's a tertiary alcohol. The functional group of an amine is an amino group. In amino group, a nitrogen atom is bonded to 1, 2, or 3 carbon atoms by a single bond. In primary amines, the nitrogen atom is bonded to 1 carbon. In secondary amine, the nitrogen atom is bonded to 2 carbons. And in tertiary amines, nitrogen is bonded to 3 carbons. The functional group of both aldehyde and ketones is the carbonyl group, which is carbon bonded with oxygen with a double bond. In aldehydes, carbonyl group is bonded to hydrogen on one side and is bonded to carbon on the other side. So in other words, in aldehyde, functional group is C double bond O and H. In case of ketones, both sides of carbonyl functional group is bonded to carbon atoms. Acetone is example of a ketone. The functional group of carboxylic acid is COOH. This functional group contains a CO and OH. So CO is carbonyl, and OH is hydroxyl. Therefore, combining these two, we get the name carboxyl. Acetic acid is an example of organic compound containing a carboxyl functional group. A carboxylic ester is commonly referred to as an ester, is a derivative of carboxylic acid in which the hydrogen of the carboxylic group is replaced by a carbon containing group. The ester functional group is represented by COO or this way. Example of an ester is ethyl acetate as shown here. Carboxylic amides or simply amides are also a derivative of carboxylic acid in which the OH of COOH group is replaced by an amine. So in other words, if we have a carboxylic group and we replace this OH with an amine, so this group is known as amide. Just like amines, amides can also be primary, secondary, or tertiary, depending on how many carbons this nitrogen is bonded to. In this case, the nitrogen is bonded to only one carbon, which is C. So hence this is a primary amide. If the nitrogen is bonded to more carbons, such as in this case, if there are carbons on the other side, then this will become an example of tertiary amide. Earlier in this chapter, we learned how a shared pair of electrons is the fundamental unit of covalent bond, and we also learned how to draw Lewis structure for several covalent molecules with single bond, double bond, and triple bond. Now we can predict bond angles and shapes of these molecules by using a very straightforward method often referred to as valence shell electron pair repulsion, or in short VSEPR theory. VSEPR theory is based on two concepts. First, atoms are surrounded by regions of electron density, and secondly, regions of electron densities repel each other because they have similar charges, or in other words, negative charges. We can predict the shape and bond angles of many organic molecules using VSEPR theory. For example, in case of methane, as shown here, the central atom, which is carbon, is surrounded by four regions of electron density. So four regions of electron densities, they organize themselves in a tetrahedral shape, and in tetrahedral shape the bond angles are always 109.5 degrees. In case of ammonia, the central atom, which is nitrogen, is also surrounded by four regions of electron density. Remember, the unshared pair of electron is also counted as a region of electron density. So hence ammonia is also ammonia also has a tetrahedral shape. Or in other words, the electronic geometry of ammonia is tetrahedral. However, because it contains only three bonds, 1, 2, and 3, shape of ammonia is trigonal pyramidal. There is a fundamental difference between the electron geometry and the molecular shape. Electron geometry is the geometry of electron regions, so which is 4 in this case. Hence the shape or the geometry of electron density is tetrahedral. However, in molecular shape we only consider the bonds, and because there are only 3 bonds in ammonia, hence the shape of ammonia is trigonal pyramidal. Similarly, in water, we have 4 regions of electron density, so therefore the electron geometry is still tetrahedral. However, shape of water molecule is also known as bent. In any of these 3 shapes, the bond angles will always be about 109.5 degrees. If a molecule has 3 regions of electron density, then the uh, geometry of electrons will be trigonal planar. Remember, double bond also count as a single electron density. Although it's a double bond, it's still 1 electron density. So this carbon atom has 3 electron densities around it. So hence the shape is trigonal planar. Similarly, this carbon has 3 electron density, and this oxygen also have 3 regions of electron density. One region is the bonded electrons or shared electrons. The other 2 regions are the unshared electrons. So the electron geometry around oxygen is also trigonal planar, and same goes for this nitrogen. If a molecule has 2 regions of electron density, then the shape is linear. The examples of linear shapes are shown here. In linear shape, the bond angle is always 108 degrees. In trigonal planar, the bond angles are always 120 degrees. Now we can combine our understanding of bond polarity and molecular geometry to predict the polarity of a molecule. To determine if a molecule is polar or not, we need to determine if the molecule has a polar bond. In case the molecule does not have any polar bonds, the molecule will be nonpolar. However, if a molecule does have a polar bond, it does not automatically means that it will always be polar. Because in case a molecule has a polar bonds, then the arrangement of these bonds in the space also plays an important role, because many times these polar bonds are arranged in such a way that they cancel each other's polarity. In that case, molecule will become nonpolar. From the arrangement of polar bonds in space, we determine the molecular dipole moment. Molecular dipole moment of a molecule is the vector sum of the individual bond dipole moments in a molecule. Molecular dipole moment is also reported in Debye. So what is the meaning of a vector sum of dipole moments? Consider, for example, if we have 2 dipole moments, one is pulling to the left side and the other one is pulling to the right side, and they are equal in strength. So in this case, although we have 2 dipole moments, but because they are in opposite sides, so the vector sum of these will be equals to 0, because in opposite sides 2 forces will cancel each other out. If 2 dipole moments are at an angle such as this way, in this case the resulting vector sum will be somewhere in the middle. So this is the meaning of vector sum of individual bond dipole moments. We will see later on that in case of molecules, if we have multiple polar bonds, in some cases the dipole moment will cancel each other out depending on what is the shape of the molecule. In other cases it will enhance or will not get cancelled. So the molecules in which the polar dipole moment cancel each other out, those molecules will become nonpolar even though they possess polar bonds. Let's take a look at some covalent molecules in which the bonds are polar. For example, in case of carbon dioxide, the shape of the molecule is linear, and each of carbon and oxygen bond is polar. But as we can see that one dipole moment is towards the right side and the other one is towards the left side, and both of them are equally strong. And we learned that the molecular dipole moment is the vector sum of these dipole moments, and we learned that if they are opposite they will cancel each other out, and hence the net resultant dipole moment is zero. So therefore carbon dioxide is a non-polar molecule even though it possesses two polar bonds. Similarly, if a molecule has a trigonal planar shape, in this shape also the dipole moments cancel each other out and the net resulting molecular dipole moment is zero, and in this case also the molecule will be nonpolar. Tetrahedral structure does look quite complex, and it contains four dipole moments, but the shape of these dipole moments is such that the resultant is zero. So therefore any molecule which has four dipole moments and the shape of molecule is tetrahedral, that molecule will also be nonpolar. If a molecule has any other shape apart from these three cases, that is linear, trigonal planar, or tetrahedral, and that molecule happens to have a polar bond, then that entire molecule will be polar. For example, ammonia. So ammonia does have three dipole moments as shown here, and its shape is pyramidal. It's not tetrahedral, so hence ammonia is polar. Another example of a molecule which is polar is water. Shape of water is bent because the lone pairs do not count towards the polarity. So there are two dipole moments and they are not exactly opposite, they are not linear, so hence water is also polar. The electron charge densities in a molecule can easily be computed by modern computer programs such as Spartan. So these electron density maps are called electrostatic potential or elpot maps. These maps show the relative electron density distribution in a molecule. These elpot maps help us to identify sites of chemical reactivity because they can predict which site has a negative charge density, or in other words high electron density, and which site has a positive charge density, or in other words that site will have a low electron density. The electrostatic potential map of formaldehyde is shown here. The area in blue shown in the bottom of the molecule is a relatively low electron density map. So in other words, the electron density is low in the bottom part of the molecule. So this part of the molecule is essentially carbon and hydrogen bonds. The area in red shows the high electron density. So that means that most of the electron density of the molecule, the entire formaldehyde molecule, is concentrated around the oxygen. So even though the electrons are distributed everywhere as shown in this Lewis structure, however, according to the computer model, most of this electron density is concentrated in the top part. Or in other words, because of the high electronegativity of oxygen, most of this electron density is pulled towards the oxygen. The electron density maps of water and ammonia are shown here. And we can see that in these cases also the electron density is concentrated around the more electronegative elements such as oxygen in case of water and nitrogen in case of ammonia.